Hello, my name is Nishant Rathore, and I'm going to be talking about my topic of apprenticeship learning via inverse reinforcement learning for my computer science 6915 machine learning course. Now, before I talk about inverse reinforcement learning, let me talk a little bit about in reinforcement learning. In reinforcement learning, you have an agent that can be a human or a robot that is taking some action in some environment. Now, this environment could be a simulated environment or a real world environment. And after taking an action A, it finds itself into a state called ST plus 1. And it gets a reward from the environment called RT plus 1. This reward is a numerical value given by the environment, and it finds itself into a new state called ST plus 1. And this new state, the agent takes another action and gets a new reward and finds itself in another state. This whole process continues until the agent has reached its goal or our simulated environment ended. As I can show you in the graphic, you have this agent that is trying to avoid this blockade. So whenever it tries to jumps over, it gets a reward of plus 1. When it collides, it gets a reward of negative infinity. That means the game is over. So that is reinforcement learning in a nutshell. But what if you do not know the rewards? What if they are unknown to you? What if you or have an expert that is giving you a demonstration that is showing you how to do things, but you do not have the information of how the expert is trying to maximize his or her rewards. In case of helicopter driving, you have an expert pilot that is showing you how to fly a helicopter, but you do not know how the expert is controlling in his brain, how is handling the brakes, how is handling the steering wheel, and all that information you do not know. All you have is a set of trajectories, which is a state action pair, and you're observing the expert doing things right in front of you. Your job is not only just to follow the action performed by the expert, but you also want to find the implicit reward function that the expert is trying to maximize, which is the main goal of inverse reinforcement learning. But you're also trying to find the expert's optimal policy from the set of trajectories. We will discuss an algorithm that can help us finding these things. This is the screenshot of the algorithm taken from the research paper, and I have linked that research paper in the list of references. And I'm going to come back to this method. But before I talk about this method, let's discuss some of the terminologies that can help us understand the algorithm better. We have this reward function that is a function of state to the state and features. And feature, in case of driving, you can have a feature. That means pedestrian, how many pedestrians are on the road, how the expert is slamming its brakes, and how many traffic lights are there, and how you're avoiding the traffic. All can be considered as a possible feature. So you have a vector of features, and you also have a W star, which is the relative weight between the set of features. And this vector is unknown to you. You do not know the value of this vector, and the goal of inverse reinforcement learning is to find this W star. You also have you defined gamma as a discount factor, which means that how you're going to be handling your future rewards. So if gamma is equal to 0, that means you only care about your immediate rewards. And if gamma is equal to 1, that means you care about all the rewards starting from this state up until the terminal state. You also have a policy pi, that is a mapping from state to actions. And you have mu of pi, which is the expected sum of discounted features, and after following policy pi. And the value of a policy is given by the W times mu of pi. Now, this is a very simplified version of the algorithm, but it is quite accurate. And let's discuss this algorithm. You have been given a set of trajectories, and these trajectories are coming by observing the expert's actions. And I'm going to index features by I, trajectories by J, and policies by K. I initialize my K to 0, and I also have this policy pi K that I can initialize randomly, or I can approximate using some reinforcement learning algorithm. Now, in this repeat I'm going to repeat all these 3 steps. So first one is the optimization step, in which I have the linear combination of features and weights, and I'm going to follow the states that are coming from the trajectories, and I'm going to take the action that is being taken by the expert, and I'm going to approximate some reward after following this state action pair. When I have a reward, and I'm going to get the reward for a particular trajectory and policy k, and I'm going to do the same thing for the policy pi k and try to find a reward for that. My goal is to find the maximum minimum difference of the 2 reward values. Now I'm going to get different reward values for a pair of jk, but my job is to find the minimum difference and get the maximum. I'm going to find the maximum minimum difference of the 2. So I'm going to have a reward function. I'm going to reward value here, and whatever the minimum value I have, and I'm going to keep changing this wi such that I am maximizing the difference, the minimum difference of the 2 reward values. Now, once I have this w that can maximize this difference, I'm going to store that as w star and increment my k, and going to approximate a policy pi k after following this reward function of w star and set of features. I'm gonna, as a sanity check, I'm gonna plug in this pi k into this equation, and if this margin, after plugging this value, if this margin turns out to be small enough, in fact, it is less than or equal to this epsilon value, which was set by us machine learning practitioners. And if it is small enough, then I'm going to terminate this algorithm and I'm going to return pi k. This pi k is quite close to the expert's optimal policy. This algorithm guarantees that the pi k is close to the expert's policy. Now I'm making some assumptions here, and the first assumption is the expert is demonstrating task in an MDP setting, and MDP stands for Markov decision process. That means I can calculate the next state and next on the reward by only observing the current state and the current action. An expert is also implicitly, we're also assuming that the expert is implicitly maximizing a reward function that is bounded by a value of 1. And the discount factor is between 0 and 1. And we are also assuming that the expert policy is optimal. And the algorithm also assumes that this algorithm always terminates for meeting this criteria. It is assumed that the unknown reward function, the inductive bias for this method, is expressible as a linear combination of known features. The hyperparameters are the vector w, which is changed during the iteration. And once we have found the optimal value, we set it to w star, but we change this value w, so that means that it is a valid hyperparameter. Also, the epsilon that compares the expert feature expectation to any of the policies found is also a hyperparameter. The limitation of this method is that the method is unable to find the true reward function, because there are multiple reward functions that can explain the expert's behavior. If you look at this grid world, and I have this expert, for instance, taking this 4 steps, now this behavior can be explained by either this grid, by either this reward function, or this first one or the second one. You could have this expert either trying to reach to this square or this square. But it is not guaranteed. It is not certain that which reward function that the expert is trying to maximize by just following the expert's behavior. It is also assumed that the expert policy is always optimal, and expert is demonstrating the task in a way that it is easy to find the reward function. There are some relationship to other ML approaches. There was one popular method that came out like in 1990s, where they use supervised learning methods to train a model to follow the expert trajectories, but it did not work in some dynamic environments, such as highway driving, where you have a completely new environment and the model doesn't know what actions it needs to take in the new environment. Some sample applications are definitely autonomous driving, where you can just follow the expert giving a demonstration of flying a helicopter, and you can learn and you can teach the agent how to implicitly maximize the reward function. Another application is machine teaching. That means you have a human that is giving you that is showing you how to do things, and you can also follow the pattern and teach other agents or other humans how to. You can train a model in such a way that you can teach other beings to follow the same things. So these are the list of references that I have used for my tutorial, and thank you very much for listening.